All right, this video is going to be some more notes on factoring, and I'm going to go over some specific types, two that should be familiar to you and one that is most likely brand new. And if you look at the assignment for today, it's broken up into 4 sections. I would recommend watching the video and pausing the video, and I'll tell you when to pause, and then doing that section and then coming back to the video. If you watch the entire video at once and then sit down to do the assignment, you're probably going to feel overwhelmed by the length of the video, and you're probably going to feel overwhelmed by the assignment. So the first section that we're going to talk about is GCF. This is called the greatest common factor. And over the course of the last couple days of factoring with trinomials, we didn't have any problems with the GCF, but any factoring problem you ever do, you're always going to want to check for the GCF first, because the GCF can show up in any type of factoring problem. So there are some factoring problems where the GCF is all that you're going to take, and so those are the examples I'm going to do first. Let's say we have 18x squared plus 48x. So the way that I work with the GCF is I look between the two numbers, 18 and 48, and I want to think about what number they can both divide by evenly. So if I look at these, 18 is divisible by 2 and 3 and 6 and 9. 48 is divisible by a lot of those numbers. So I'm going to think about, does 48 divide by 9? No. Does 48 divide by 6? Yes. So that's the largest number that they have in common. So I'm going to go ahead and take a 6 and put that out in front. And then I'm going to put parentheses. All right, and then between the x squared and the x, I have to think about what's in common. So x squared is like an x multiplied by an x. X is just, there's just one of them. So I'm going to think of 1x as being the GCF. And that's what I'm going to leave in the front. All right, and then everything else gets written inside, and I always think of it as the leftovers. So if I do 18 divided by 6, I get 3 left over. If I think about x squared, that's x times x. I have one of them in the front. That means there's 1 left over inside. 48 divided by 6 has a leftover of 8. The x was already in the front, so there's nothing left over. And so that right there is my final answer. 6x is the GCF. 3x plus 8 is the other factor. And factors they don't have to be written in parentheses to be considered a factor. So we would say 6x is the first factor, 3x plus 8 is the second factor. So this is the completely factored form. All right, for the second example, I'm going to write negative 7n to the 4th minus 56n squared. And this problem is kind of unique because it has a negative term, a negative leading term. And what I mean by that is the first term is negative. And a lot of times you don't see that in math. A lot of times people try to write something so that it's positive in the front. So anytime you are factoring and you have a negative leading term, you want to take the negative out with the number. So I know that whatever I have for my GCF, it's for sure going to be negative. And the second term, it doesn't matter if it's negative like it is in this case, or if it's positive, that does not matter. If you start off with a negative leading term, you're going to take a negative out with your GCF. So now I'm thinking about what's in common between 7 and 56. 7 is a prime number, so it's only divisible by 1 and itself. So that means I'm going to make sure that 56 is divisible by 7, and it is. So I'm going to go ahead and take out negative 7. And then here I have n to the 4th and n squared. N to the 4th is n times n times n times n. There's 4 of them written right next to each other. N squared only has 2 of them. So if I think about what's in common, it's only going to be 2. So I'm going to write n squared in the front. So the pattern that you'll notice with the variables is that whatever the smallest exponent is, that's what you take out. This one had an exponent of 2. This one, they didn't write the exponent, but it would be an exponent of 1. And that's smaller, so that's what we took out. Here, exponent of 4, exponent of 2. 2 is smaller. That's what we take out. All right, so -7 divided by -7 is 1. You can write the 1 or not write the 1. It doesn't matter. There was n to the 4th, so there was 4 of them to begin with. We took 2 out, so we're going to leave 2 behind, n squared. -56 divided by -7 is +8. And n squared out here, n squared in the front, that means we already took them, so there's none left over. All right, third example. So here's one where we have more than one variable, 12x squared y plus 36x. So instead of just thinking about what my numbers have in common and what my letters have together, I'm going to have to think about the numbers, then the x's, then the y's. So between 12 and 36, 12 goes into 36 evenly, so I'm going to say 12 is the GCF. Then if I compare, I have x squared and x. This is an x to the 1, and that's smaller, so I'm going to take out an x to the 1. The first term has a y, the second term does not, and so that is not a GCF. So now I can go ahead and write my leftovers. 12 divided by 12 is 1. I don't even have to write it. X squared, there's one x in the front, there's still one up here, so I have to write that x. There's a y up here, there's no y in the front, so there's still a y left over. 36 divided by 12 is 3. There's an x up here, it's already taken out in the front, so it's not a leftover, and so now I'm done. Okay, so those are problems where there is only a GCF, there's nothing else you can do. One of the clues that I notice when I see problems that are only GCF is that oftentimes they have 2 terms. They could have 3 terms, but often if they have 3 terms, it means there's something else we should do to factor. So problems with 2 terms a lot of times only have a GCF, although we will be looking at difference of squares, and that has 2 terms but still has another piece to do. Okay, so these next couple examples are taking what we've done from the last few days and are just adding in that the problem has a GCF before you continue the rest of your factoring. So 3x squared plus 3x minus 126. The common mistake that I find with problems like this is students think that because there is a 3 in the front, this is a slide divide problem, and it's not. And the reason that it's not a slide divide problem is because we have a 3 here and a 3 here, and that's a GCF. And if you look at negative 126, it's actually divisible by 3. It's negative 42. So what I'm going to do is I'm going to take the 3 and I'm going to put the 3 in the front, GCF of 3, and then I'm going to write my leftovers. So if I take out the 3, I have an x squared. If I take out the 3, I have an x. If I divide by 3, I have negative 42. So now, if I ignore the 3 in the front and I just look at what I have here, I'm looking for 2 numbers that multiply to negative 42 that add to positive 1. And the 2 numbers that do that are 7 and negative 6. So I have x plus 7, x minus 6. And because it's just an x squared all by itself, it's not a slide divide problem. This is just normal trinomial factoring, a equals 1, easy peasy. Now, before I say that I'm completely done with the problem, I do have to take that GCF of 3, and I have to stick it in the front of my final answer. And now I can say that I'm done. All right, with this one, 5v to the 4th minus 40v to the 3rd plus 35v squared. So when I look at this problem, before I even get started, I wouldn't have been like, oh, I should do the normal trinomial factoring on this, because the exponents on the v's are a little bit too high for me. V to the 4th, v to the 3rd, we didn't really deal with that. So if you look at this, they all have v's in them, which means that v is a GCF, and in fact, the smallest exponent of v is v squared. So v squared is the GCF. And then if I look at the numbers, I can see that they're all multiples of 5. So 5 is also part of the GCF. So I'm going to write 5. The smallest exponent of v is v squared. And now I can go ahead and write my leftovers. So I took the 5 out, that's gone. This is v to the 4th, and I took 2 of the v's in the front, so now I've got 2 left over. Negative 40 divided by 5 is negative 8. There are 3 v's, but I took 2 of them out, so there's 1 left over. 35 divided by 5 is 7. V squared, I took v squared out, so it's gone. So now I'm going to go ahead and ignore that GCF in the front. And I'm looking for 2 numbers that multiply to positive 7 but add to negative 8. And the 2 numbers are negative 7 and negative 1. So v minus 7, v minus 1. And then I go ahead and I stick that GCF back in the front. And the problem is completely factored. All right, for this problem, we do not have a GCF of the variable. X squared, x, and no x is normal for us for factoring. But if I look at this, I see 8 and I see 4. And so that means that 8 is not the GCF. So when I take the GCF out of this problem, it is not going to leave me with the squared term by itself. It's going to leave me with a number in front of the squared term, and that's how I know that I'm about to do a slide divide problem. So 8 is divisible by 4, 4 is divisible by 4, negative 112 is divisible by 4. So I'm going to go ahead and take a GCF of 4 out. And then I'm going to write my leftovers. So 2x squared plus x minus 28. And then I'll go ahead and do the rest of the slide divide problem. So when I get down and I have my GCF taken out, if there is still a number in front of x squared, that's how I know I'm doing a slide divide. So 2, slide it over to the negative 28. That gives me negative 56. So I'm looking for 2 numbers that multiply to negative 56 but add to positive 1. And the numbers are 8 and negative 7. And so now I'm going to go ahead and write x plus 8, x minus 7. So I did the slide part, now I have to do the divide part. The number that I divide by is the number that I slid. So divide by 2, divide by 2. I can see that 8 divided by 2 is 4. X plus 4. And then the other fraction is 7 over 2, and I can see that on that fraction I need to do a bottoms up. So I'm going to take the 2, move it to the front. 2x minus 7. And then to say that the problem is done, I just have to go back and take the GCF and move it down through the problem. So keep my GCF of 4, keep my GCF of 4, and I'm done. So you can see that when you're working with the GCF, once you take it out, you kind of ignore it. You do the rest of the problem as though it's not there, and then you just stick it in the front at the end. All right, one more example before you pause the video and work on that section. So we've got 42b squared minus 6b minus 48. And my clue here that of my GCF is the middle term 6. That's, the only thing the biggest thing that can divide into 6 is 6. I can't get any bigger than that. And so if I double check to see how it works with these two, I can see that 42 divided by 6 is 7. And 48 divided by 6 is 8. And so that means that my GCF for this problem is 6. So I'm going to go ahead and take out the 6 in the front. And then that leaves me with 42 divided by 6 is 7b squared. 6 divided by 6, the 6 goes away and I just get negative b. 48 divided by 6 is 8. Oh, this problem's kind of similar to the last one. So this is a slide divide problem, I can tell, because there's still a 7, there's still something in front of the b squared. The reason that I was saying this problem is similar to the last one is because 7 multiplied by -8 is -56. So just like that last one we did, and we're multiplying to -56 and adding to -1 this time, which means we're using the same two numbers, we're just switching them. So -8 and +7. So I've got b minus 8, b plus 7. And then now I have to do the divide part. So 7 is the number I slid, 7 is the number I'm dividing. And for my second set of parentheses, I can see 7 divided by 7 is just 1. But for my first set of parentheses, I need to take this and move it up to the front. I got bottoms up. So 7b minus 8. And then because I had that GCF in the front, I just have to go back and make sure that I write that through each step. So GCF of 6, GCF of 6, and I'm done. All right, so at this point, you should pause the video and you should work on the assignment, and you're doing problems 1 through 8. So pause the video and do 1 through 8. All right, for the next part of the video, we're going to be doing difference of squares. And when we look at difference of squares, the way that you're going to see the problem is you're going to see one squared term subtract another squared term. And it could be variables, but it's also going to be perfect squared numbers. So we're going to put an equal sign up here. The types of numbers I'm expecting to see is like 1 squared is 1, 2 squared is 4, 3 squared is 9. So these are the types of numbers I'm expecting to see. And I'm going to go ahead and make a list because some students don't have these memorized. And it would be good to have them written down so that you can recognize them when they happen. They get a little bit more difficult after you get past 100. Thirteen squared is 169. 14 squared, I believe, is 196. Let me check on my calculator. Yes. And then 15 squared, ooh, 225. Ooh, sweet. Okay. So these are just the starting ones. I think that should be enough to kind of help you with the assignment today. But when you see this, the difference of squares, your factors are a plus b and a minus b. Those are your two factors, a plus b and a minus b. All right, so here are some examples. If we have 49x squared minus 64. So I can tell that this is a difference of squares factoring problem because 49 is a perfect square and 64 is a perfect square. So when I factor this, I do two sets of parentheses, one with a plus, one with a minus, and I just look at the perfect square and I figure out what its square root is. So if 49 is the perfect square, the square root of 49 is 7. So I see a 49 here, so I'm going to put a 7 and a 7. X squared, so I'm going to put an x and an x. 64, the square root of that is 8, so I'm going to put an 8 and an 8. And then I'm done. That's it. 7x plus 8, 7x minus 8. All right, example 2. 9n squared minus 100. So again, I recognize that the 9 is a perfect square, the 100 is a perfect square. And so I do two sets of parentheses, one with a plus, one with a minus. The square root of 9 is 3, so I'm going to put a 3 and a 3. I have an n squared, so I'm going to put an n and an n. And then the square root of 100 is 10, so I'm going to put a 10 and a 10. 3n plus 10, 3n minus 10. All right, 28a squared minus 7. Now, when I look at this problem, this does not quite look like difference of squares because 28 is not a perfect square and 7 is not a perfect square. The thing that's making me think of it as difference of squares is that a squared is a perfect square, right? It's a times a, and this has a minus in it. So even though the numbers aren't right, it kind of looks like that form, and that tells me that maybe I should check for a GCF. So if I look at 28 and I look at 7, well, 7 divides by 7. If I think about 28, 28 divides by 7 as well. So I'm going to go ahead and take 7 out as a GCF. 28 divided by 7 is 4. So I've got 4a squared. 7 divided by 7 is 1. And this time, the other times I didn't have to write the 1 if the number was out in front, but that was if there was a variable that I could stick after that. This time there wasn't a variable, so I had to put a 1 there, and some teachers describe that as a placeholder. If I didn't put the 1 there, I would just have 4a squared minus, and that would be weird. You want to have like just 4a squared minus. So 7 divided by 7 is 1. I'm leaving the 1 there. Now, if you look at our list, 4 and 1 are both perfect squares. So that means that this really is a difference of squares problem. And so I'm going to do 2 sets of parentheses, one with a plus, one with a minus. The square root of 4 is 2. So if I look at my list, square root of 4 is 2. And then I have an a and an a. The square root of 1 is 1. And then I just go back and I take my GCF and I stick it in the front. All right, here is the 4th example. And I wanted to include this one because I thought the numbers made it look real tricky. I did not like these numbers at all. And I thought if we have numbers we don't like, we should definitely try to do those. So with something like this, these numbers are pretty big. I'm going to go ahead and deal with the smaller one because whatever the biggest number is that goes into the smaller one, right, it can't be any bigger than that to go into the larger one. So I just start doing, actually we can do our little divide trick. The reason I'm going to do this is because this is going to show me what numbers are divisible, what numbers go into 175. So 175 is divisible by 1, but not 2, not 3, not 4. Okay, it's divisible by 5, but 847, I can see that that's not. It's divisible by 7. That's about it. Look at all those decimals. It's divisible by 7. So let's go ahead and check. 847 divided by 7, that's our number right there. Okay, so we're going to take out a GCF of 7. And 175 I mean, divided by 7 is 25. 847 divided by 7 is 121. And I know that these are good numbers because they show up on that list. I've got 25, I've got 121. The reason I could kind of tell that was my goal with the original problem is because, again, I had those two terms, I had the negative in the middle, I had the n squared. So even though the numbers were a little bit confusing, it still looked like it was kind of going to fit that form. So now that I have my two perfect squares, I can go ahead and do 2 sets of parentheses, one with a plus, one with a minus. And the square root of 25 is 5. And then I've got the n. And 121 is going to be 11 and 11. All right, and then I can go ahead and put the 7 in the front, and I'm done. So at this point, you should be pausing the video and you're going to work on problems 9 through 14. 9 through 14. And within those problems, 9 through 14, there is one trick question, and I want you guys to see if you can find it. So 9 through 14, that's what you're working on next. All right, the next set of notes that we're going to take is over the sum or difference of cubes. Sum or difference of cubes. So here is the formula for this. We have a cubed plus b cubed, that's the sum. And we have a cubed minus b cubed, that's the difference. So the first set of parentheses is just a plus b. Here the first set of parentheses is a minus b. The second set of parentheses is a little bit trickier, but there's a pattern to it. So you do a times itself, a squared. Then whatever this sign is, you do the opposite. So if this is a plus, this one is a minus. Then you multiply the two together, a times b. And then the last term is always a plus, always positive. And then you do this term multiplied by itself, b squared. So we do the first term multiplied by itself, a squared. We do the opposite sign. See, these ones match. We do the opposite sign. Then we do the two multiplied together, ab. And then it's always a positive. And then we do this one multiplied by itself, b squared. Now, the way that I remember the signs is same sign, opposite sign, always positive. So you'll hear me say soap when we do these problems. All right, again, we want to know what the perfect cubes are. So we've got 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 25, 6 cubed is 216, 7 cubed is 343, I believe. That's about as far as I have them memorized. 8 cubed, let's find this out together. 8 cubed is 512. 9 cubed is 729. 10 cubed, I know this one, it's 1,000. That's probably about as high as we need to go for these. Okay. So to do these problems, the first thing we have to do is kind of break the numbers down. So if I look here, here's my first example. I'm going to say 27u to the third minus 8. And to start this problem, I want to rewrite each of those numbers so I know what my a is and I know what my b is. So I'm going to write this as something cubed minus something cubed. So 27 is 3 cubed, and we have a u as well. So I'm going to go ahead and write 27 is 3, so I'm going to write 3, and then we have the u. 3u cubed. Okay, and then 8 is 2 cubed. So I'm going to go ahead and put a 2 there. All right, so now I'm going to go ahead and follow my pattern. So the pattern says I keep the same, I'm going to write soap. I'm going to keep the same sign, a minus b. So I'm going to have a, 3u, minus b, minus 2. Okay? Then I have a multiplied by itself, a squared. So that is going to be 3u multiplied by 3u. Then I have the opposite sign, so plus. Then I have a multiplied by b, so 3u multiplied by 2 times 2. And then I have always positive, and then I have 2 multiplied by itself. So I'm doing the colors because I hope that you guys can kind of see how it works. So A minus B, A multiplied by itself, plus sign, A multiplied by B, plus sign, B multiplied by itself. So my final answer is 3u minus 2. 3u multiplied by 3u is 9u squared. 3u multiplied by 2 is 6u. 2 times 2 is 4. And then I'm done. All right, example 2. This one, 729m cubed plus 125. So these are good numbers. I recognize these from the list. 729 is 9 cubed. 125, oh, I wrote 25 there. Oh, goodness, that's a 125, not a 25. Sorry, guys. Okay, 125 is 5 cubed. So I'm going to go ahead and rewrite this. We've got something cubed plus something cubed. So the first one, 729, we said that was 9m cubed. And then over here we have 5 cubed. Okay, so I'm going to follow my pattern. We're doing the plus version this time, so I'm doing the top line. So first I have A plus B. So 9m, A plus B. Plus, keep the same sign as the problem, plus 5. All right, then I have A multiplied by itself. 9m times 9m. Okay, now I have the opposite sign, and I have A multiplied by B. So times 5. And then I have always positive, and I have B multiplied by itself. So A, same sign, B. A times itself, opposite sign, A times B, always positive, B times B. So there's a definite pattern there. All right, so we have 9m plus 5. 9m times 9m is 81m squared. 9m times 5 is 45m, and then 25. And we're done. All right, example 3. 500m to the third plus 864. Again, these numbers are ginormous. And when I look at this, these are not the numbers that I like. These are not those perfect cube numbers. And since I can see something cubed plus something else, it kind of fits the format that I was looking for, which means that this is a GCF problem. So I need to figure out what number divides into both of those. Now, between the last couple examples and this one, I actually thought of a trick that I'm pretty sure is going to work. So I'm going to do 500 divided by x for y1 and 864 divided by x for y2. And I'm going to hit second graph. Now it's going to give me 2 results. I'm going to go ahead and compare these. So I'm going to go back up. Okay, so what I want to do is I want to see what number works for both of them. So they have a common divisor of 1, but that's not helpful. So 2 goes into both. 3 goes into 864, but it does not go into 500. So now we can see 4. Not 5, we got a decimal over here. Not 6, we got a decimal there. Decimals, decimals, decimals. So we can see like it goes in there. Yeah, so let's go back to what we had. There was one where we had good numbers on both sides. We had these. No decimal, no decimal. And if you look at the numbers 125 and 216, those are good numbers because they're on our list. 125 is a perfect cube, 216 is a perfect cube. So what I'm going to do is I'm going to take out a GCF of 4. And the reason I'm going to do 4 is because that's what I saw on the table, 4. All right, so I've got 4 as my GCF. And then that leaves behind 125 m to the third plus 216. Okay, so I'm going to keep that. I'm going to go ahead and write this as something cubed plus something cubed. And so 125 is 5, so that's 5m to the third. 216, that's 6. All right, so now I'm going to go ahead and use my pattern. I have A, keep the same sign, and B, so keep the same sign, and B. And then I have A multiplied by itself. I do the opposite sign, and I do A multiplied by B, and then I have always positive, and B multiplied by itself. All right, so 5m plus 6. 5m times 5m is 25m squared. 5m times 6 is 30m. 6 times 6 is 36. And before I say I'm done with the problem, I have to go back and bring that GCF all the way down. Whew. Okay, so the section that this applies to is that third section. That's problems 15 through 20. 15 through 20 are all like this. And then when you're done with 15 through 20, you have section 21 through 30, which actually messes up, it mixes up all those problems, and it's just everything. It's a little bit of all of it. And so there it'll really test, can you recognize what you're doing? So again, the way that you kind of recognize it, GCF is typically just 2 terms. This one, you'll notice that there's typically exponents on both of the variables or both of the terms when we do GCF, but they're often just like 2 things. Here we have our trinomials that have a GCF, so now when we do these problems, we're just always going to check for that. We're never going to ignore that anymore. We're always going to look for a GCF. When we have difference of squares, we're going to look for these specific numbers, and we're going to look for something squared minus something squared. That's going to be typical for us. And then sum and difference of cubes, you can kind of recognize those because, again, they're 2 terms, but they're cubes. So they're a little bit easier to see. So those are the things that we're going to look for in that very last section so we can recognize what type of problem we're doing.